Welcome back, guys. Tonight we're cracking open this 1836 Geography of the Heavens by Elijah H. Burritt, accompanied by a celestial atlas, which we don't have in person, but I was able to actually track down through the Internet Archive a super high-def version of the accompanying celestial atlas. And tonight we're going to be looking at this book through the lens of modern astronomy. We're going to look and compare the nearly 200-year-old, for those nitpickers out there, 200-year-old astronomy, the information, what they knew, with modern understandings, to the extent that we can say we understand the physics, astrophysics of what's going on out there. So our focus tonight is going to be chapter 13 in this book. But before we get into that, I just want to briefly give a thanks to our second ever sponsor. A shout out and a thank you to Manta Sleep Mask. I decided way back when, when hitting 100,000 subscribers was still very much a pipe dream, that I wanted to endorse a product, if I ever would, that I personally used and I personally really had faith in. For those of you not familiar with what a sleep mask is, when I got this sent to me and I tried it out for the first few nights, I was just blown away by just this visceral sense of calm. It's like almost taps into the childlike sense of, nuzzling up to someone. The way they designed it, of course you can hear the beads going in it, but it's got seams running down the front of it. And so the weight itself, the beads don't clump up in any one particular area. You can see it fits around my strong European nose. This thing fits so snugly around my face, I don't even know it's there after I'm wearing it for a little bit. I really can't praise this product enough. It's worked wonders for me, and I only started off using it a couple of nights a week, and now I kind of just find myself grabbing it every night. I had warned you guys not to check out the product if you are interested, because I have a promo code right now, actually, in this video. It's Let's Find Out, all one word. Enter that at the, if you're watching this on YouTube, the link will be in the description below to get 10 or I think it might be 15% off. But their masks are already affordable as it is. So, Manta Sleep, thanks again for sponsoring the channel. Alright, so let's put that aside. Get back to the topic at hand. We're going to learn about stars and what Elijah Burritt coalesced from the knowledge of early 19th century, 1800s astronomy. Always smiling because I always have the intention of making things into a series and returning to them, but many things I don't come back to. But if we do, tonight will be the first in a series exploring comparing the knowledge gap across 2 centuries of time. Tonight's video is going to focus on chapter 13, which is primarily revolving around stars, but in particular from the point of view of this book, it's going to be stars, binary stars, star clusters, and lastly, the 4th section, it's going to be nebulae. And keep in mind, this was probably 100 years before the radical realization, primarily from the work of Edwin Hubble, the great astronomer after whom the telescope is named. The discovery of galaxies was 100 years away in this book. So what they call nebulae is a nebulous classification of celestial objects, into which galaxies are but one of the subcategories of the book. Okay, so let's open this up. again, are personalized to Dad from 1970. I love thinking about how many hands this book has probably been through. So, we're going to go to chapter 13. Let's find this where we are. You know, I've done a little background research, so I got the laptop right there, ready to go. And what we're going to do is take it almost point by point. We're going to find section by section what he points out, little details and facts and things he focuses on, so that we can kind of jump from there to the current era. So here, our index, unlike modern table of contents, they kind of just throw the index at the beginning instead of a orderly table of contents going in consecutive page order. So we got to go alphabetically. And chapter 13 is on stars. So we're going to be starting on page 137. Let's find that. Oh, and look at that. So he actually, it's like 2 books in one almost. I forgot about that. It's been a while since we recorded our last part. It's interesting that, because the bulk of, I guess, part 1 is on the constellations. How to find them, how to, spot them, their mythological backgrounds. And then at the very end of part 1, chapter 13, he broke them up into the 12 zodiac signs. The first, chapter about non-observational astronomy, a little more about concrete classifications of objects we'd see more similarly in a modern-day astronomy book. He starts at the end of part 1. You would think he would kind of section that into book 2, but anyways, on page 137 here we got chapter 13. He breaks into 4 sections. We have 1, variable stars, then we have double stars, clusters. Where's that? There we are at the top of the page. Clusters on top right there. And then lastly, section 4, nebulae. Chapter 13 here starts with section 1, variable stars. The periodical variations of brilliancy to which some of the fixed stars are subject may be reckoned among the most remarkable of their phenomena. Several stars formerly distinguished by their splendor have entirely disappeared. Others, now conspicuous, which do not seem to have been visible to the ancient observers. So some have disappeared. Some seem to have arisen out of dark patches, black voids in the sky. And there are some which alternately appear and disappear, or at least of which the light undergoes periodic changes. Some seem to become gradually more obscure, as Delta in the Great Bear, and others like Beta in the Whale seem to be increasing in great splendor. Great splendor, great splendor. And after a gradual diminution of their light, again become extinct. So, beta and, let's see, delta in the great bear and beta in the whale. Now, I want to try not to make this into just about the constellations, but I do want to put everything we're reading in the next few pages into context. And again, channel, I named it Let's Find Out because I like to challenge myself and learn new things. And as interested in astronomy as I've always been, I've actually never been interested in learning about the constellations. I guess I didn't like it because of its the mythological, but more importantly astrological undertones, because I didn't like the superstitious undertones that come with astrology and knowing your zodiac signs. And as Carl Sagan famously disputed, the superficial labeling of personality traits based on the particular alignments of the planets and the stars during which month and year a person was born. Now, I'm still not convinced really at all by the influence on a particular person's personality that might have. But after reading in particular Carl Jung's book Ion, I am much more open to the projection that the ancients had, especially pre-scientific ancients, the projections of psychology, psychological archetypes, and unconscious ideas and motivations that the ancients did and significantly projected onto star patterns in the cosmos, and how those seem to have influenced history, at least to some extent. But I guess that's for another episode, about how Ion being the revolution of the zodiacal signs, and how they do align, and the wobble, the precession of the equinoxes completes a full rotation every 24,000 years. That would mean that every 2,000 years, and it's been roughly 2,000 years since the birth of Christ, there is a new eon or ion that is in a particular part of the sky at a particular time. And so that changes every 2,000 years due to the wobble of the earth on its axis. And right at the time of Christ, this is a little side note, the age was which was it? So we recently are about to, or recently did, because it's a 2,000 year phenomenon. You can't say there's an exact date. The fine transition period is a little broader than just one day. It's maybe a couple centuries, But Christ, we're in the age of Aquarius. Christ represented the age of Pisces, the fish. That's why the Christian symbol is the fish. And so often it's both the cross, but it's also the fish. He was known as the fisher of men, for instance. He was able to, and there's many allegories, parts in the Bible where Jesus was able to do certain miracles that involved fish. And then I believe before him it was the age of was it the goat? Let's see. So in Carl Jung's book, Ion, researches into the phenomenology of the self, he tried to make a case for Christ as being the fulfillment of an expected or prophetic tradition. And I guess without getting too deep into it, it's just interesting as a guy who studied psychology so thoroughly and wanted to extract the most value out of religion, the traditions of alchemy, astrology, mysticism, and Gnosticism. He recognized that before science we didn't have any methods for reaching an objective truth the way science currently does. So he was looking through the old texts, realized that, as we can see here, the astronomical symbols goes Gemini, Taurus, Aries, and then Pisces. From 2000 BC to the year 0, when Christ was born, that was supposedly the age of the ram. In these 2,000-year cycles, it had a transition roughly around the year 0, when Christ bore in the new millennium, the new ion, rather, and he represented the dying ram in the birth of the fish in the age of Pisces, which now has just concluded, or is in the process of concluding. And then, as you see here, Pisces turns into Aquarius down here. So Carl Jung was interested in how ideas can propagate through cultures, and what these ideas mean for what goals a culture has. So the Jewish culture and the tradition that Jesus was a revolutionary prophet in had its series of prophecies that were waiting to be fulfilled. So you can say that centuries, even millennia of thought and effort and cultural development and religious speculations were put into what Christ ultimately became. And so Carl Jung's point was that the assumption that certain things were going to happen in a weird way makes some things happen sometimes. If people want something bad enough, sometimes they get it. And sometimes when they're looking for patterns hard enough, they see it. Even if objectively there might not have been that pattern there to the person who wasn't looking for it. So anyways, the reason I brought that all up was because Jung wrote an entire portion of this book, if not kind of the whole book itself, really, of Ion in his later years, trying to understand where the origin, why would this symbol that is part of astrology, how did that attach itself to a figure on Earth, and how did it come to be identified with a human being, who claimed to be a great moral prophet, bringing in new values to the human species, at least to a section in the Western world. How did he come to identify with the fish? Jesus was born as the first fish of the Pisces era and was doomed to die as the last ram or lamb of the declining Aries era. Yeah, here, a direct astrological aspect of Christ's birth is given us in Matthew 2, verse 1. The Magi from the east were stargazers, who, beholding an extraordinary constellation, inferred an equally extraordinary birth. So, to me, that's all very interesting. The influence that the stories and mythological characters we projected onto the stars and for human lifespans, eternal stars in their eternal positions. Something we can latch onto, something that is unchanging throughout many human generations. So it acts as a stone, a uneroding stone in which we can inscribe our human stories and our narratives and our evolved and transmitted wisdom. And again, pre-1900, everywhere you went, the star, as long as it wasn't cloudy, even with a full moon, I'm sure, was absolutely lit up with the hundreds of thousands of sharp points of light beaming in the night sky, which you can only imagine how much that must have infused the human imagination with wonder and awe and speculation and a desire to know more about the world and create stories, tell stories, share ancestral wisdom around a campfire. Even the longest stories, like the Iliad and the Odyssey and Gilgamesh, were only transmitted orally. And in order for that game of telephone to not distort the fundamental truths that we sought to transmit, that were so hard-won over generations, that the values and wisdom that we couldn't afford to lose as a culture, as a civilization, in order for those to not get lost and distorted, it was very important to have a widely agreed upon series of myths and stories that were imprinted onto an objectively existing external phenomena like the stars. Even mountains can erupt and erode and have landslides. Rivers can change their course and meander in different directions, even within a generation or two. Climates can change, but the stars, in human terms, the stars are eternal and unchanging. The last thing I said here was the connection between, myth and astronomy and stars and the cosmos is significant because astrology was astronomy back in the day. The two were not yet separated and distinct. They were the same thing. So if you were to study the stars, you necessarily had to understand the stories that are linked to those stars. Knowledge was stored, so to speak, in the stars back then. And therefore, all that equaled the wisdom in antiquity, the wisdom of antiquity. So a narrative as potent as Christ's, at the dawn of a new ion, initiated a chain reaction of belief, spirituality, and hope. So the idea that someone was a prophet is very much influenced by expectations, which are in turn influenced by the stories cultures tell themselves. So, in other words, we already kind of we're primed as a culture, especially back then, pre-scientific, mystical, and supernatural phenomena happening all around us, very wanting to believe, very ready to believe in something that shows qualities of a divinity. So I was very much interested in Jung's interest in why Christianity stuck and became so popular in the way that it did. So our first constellations we're going to be looking at are Delta, the Great Bear. We want to look at Delta in the Great Bear, and the general mechanism for naming stars is to look at the most prominent stars in those constellations and name them the letters of the Greek alphabet. So Delta was a variable star that seems to become gradually more obscure, whereas Beta in the Whale is increasing in its brilliancy. So variable stars are, in modern astronomical terms, what we understand them as is a star whose brightness, as seen from Earth, meaning its apparent magnitude, because it's as opposed to its intrinsic magnitude, which would be its objective brightness, because we are representing one vantage point on Earth from the cosmos, and the star's brightness might change if we are, depending on our distance, depending on any nebula, gaseous clouds, or our atmosphere blocking the light. So, as it appears from Earth, a variable star is a star whose brightness fluctuates as seen from Earth. This variation can be caused by a change in emitted light, or by something partly blocking the light. So variable stars are classified, again using the intrinsic-extrinsic distinction I just made, as intrinsic variables whose luminosity actually changes, for example, because the star periodically swells and shrinks. Extrinsic variables, on the other hand, are stars whose apparent changes in brightness are due to changes in the amount of light that is able to reach Earth. For example, a star has an orbiting companion that might sometimes eclipse it, at least from our perspective. So if we happen to be exactly on the plane of the orbital path of a binary system, or a star with a really large planet, those two objects are going to seem to eclipse each other. So what was that called? Occulting, I think. Many, possibly most stars have at least some variation in luminosity. The energy output of our sun, for instance, varies by about 0.1% over an 11-year solar cycle. So here we see this picture of the Big Dipper right here, and Delta. And so in this book, the way they the nomenclature, and that was the word I was looking for earlier, the nomenclature that Burritt gives in his book here is the Greek letter and then the name in which that Greek letter of the name of the constellation in which that star exists. Nowadays we have oftentimes either the technical designation of the star, which is like an acronym with some long list of numbers after it, or it's a individually named star. So Delta in the Great Bear is, I guess I'll just click the link to show you. the Great Bear. How are we not connected? The Big Dipper is the tail of the Great Bear. So let's open this and show you guys. There we go. Good example here. So right there, we have our 3 main stars in the tail, and then the 4 main stars making up the, zoom in even further, making up the body, or at least the hindquarters of the bear. And the bear is called Ursa Major. Ursa meaning bear, major meaning big in Latin. Oh, and there's a manta sleep. So in the star we're looking for, Delta in the Big Bear is called, it's right here, called Megrez. Megrez. So this star has an excess emission of infrared radiation, indicating the presence of circumstellar matter. So this forms a debris disk around an orbital radius of about 16 astronomical units, or distances from our distance from the sun, about roughly 90 million miles. So 16 times the Earth's distance from the sun, astronomical units, or AU, is about how far out Megrez's circumstellar orbital disk of debris is orbiting. So Megrez actually has 2 faint companions, a 10th magnitude star and an 11th magnitude star. So both at an angular separation of 2 arc minutes from the primary. And by the way, Megrez, coming from the Arabic al-Magriz, the base, meaning the base of the bear's tail, is an indication, just this one of many stars that we're actually going to be seeing today that have its name derived from an Islamic word. So just like there's many stars of Latin origin in terms of their name, there is actually, in the Islamic Golden Age of our Middle Ages in Europe, there were many great astronomers and thinkers and early proto-scientists whose knowledge was in one way or another transmitted to the European civilization in the late Middle Ages. So yeah, so now we know Megrez actually has 2 faint companions, and they just orbit so slow that it just happened to coincide at the time of the last century or so of observations, according to Burritt here, that Megrez, or Delta in the Great Bear, was becoming gradually more obscure. So perhaps both the binaries were. And apparently Megrez is about 63% more massive than the sun, giving it a radius of about 1.4 times the sun as well. I can't find how long it takes them to orbit it, but from what I found, a lot of the orbits are actually kind of, well, I guess you can imagine, whether it's the companion stars or the circumstellar disk that's creating the obscurity, anything out that far, given that it's about, was that roughly the same orbit as Jupiter? Or no, Saturn, I guess. Let's see, Saturn orbital distance. about 9.9 AU. So I actually think Uranus orbital distance is in AU. So Uranus is about 19.8, so almost 20 AU from the Sun. And Uranus's orbit duration, 84 Earth years. So you're looking at a anywhere from maybe 60 to 150, something like that, orbital period orbiting this Megares star, creating its variability, so to speak. And let's see now. Okay, so Beta now, this was the one that Burritt says seemed to be increasing in brightness. So Megares was gradually becoming more obscure. Beta in the Whale, is the constellation Ceti, or Ceti, C-E-T-I. So Beta, so those would be Beta Ceti. How do I pronounce that? Let me see. Does it say? No, it doesn't. Or we could call it Difta. That's another name. It's the brightest star in the constellation. So Beta is right here. It's at the base of that triangle right there, of constellation Cetus, I guess. Although designated Beta, it's actually brighter than the Alpha star in the constellation, Alpha being right there. On these maps, the size of the star designates its magnitude. Oh, and that's the other thing. The two faint companions of Megares, it said they were 10th and 11th magnitude stars. That is, in general, on a scale that means the larger the number is the more faint, smaller the number, going all the way into the negatives even, means a more luminous, more bright star. So, for instance, Venus and Jupiter being the brightest, what do you say, normal objects in the sky, regular objects in the sky, meaning something like that regularly occurs as opposed to a supernova, one-off events. Those actually have negative magnitudes. Magnitudes meaning brightness. So Beta in the Whale, so our Difta or Beta Ceti, it displays flaring activity that results in random outbursts that increase the luminosity of the star over intervals lasting several days. So it's interesting that Burritt in the book picked these two stars because they're great examples of their respective extrinsic and intrinsic variability. Beta in the Whale here being an intrinsically variable star because its own properties are what create the variability in its luminosity, whereas our Megares or Delta in the Great Bear was only varying from our perspective because there was a debris blocking its light from reaching us. So our Difta has our Beta in the Whale here, Beta, has random outbursts that last several days. This is a much longer duration than that comparable to our own solar flares that we see on our star, which only last typically about a few hours, or at least durations measured in hours rather than days. So let's see, what else did I say here? And then actually, this was another kind of difficult one to track down, because in the whale constellation Cetus, there's a star called Mira. You'll notice here, it's the only star with a proper name, with its own name that's not a Greek letter. And I almost mistook that for beta, Burrett's beta in the whale here, for Mira, also called Omicron Ceti. Its Greek letter is Omicron, because in 1596, in fact, it's on the front page. If you look up the Wikipedia page for variable star, Omicron Ceti, or Mira, which I think is would be kind of a cool name. I know it means look in Spanish, but it's on the top. It's kind of the, what do you call it? It's the primary example of a variable star, because in 1596, Mira, Latin, which is Latin for astonishing, had been described as a nova, but would later become the first non-supernova variable star discovered when Johannes Halwarda noticed it pulsating, taking 11 months, an 11-month cycle. Mira combined with supernova of 1572 and 1604, a very, that was the time around Galileo and Tycho Brahe and I think Copernicus. That was the late stages of Copernicus's life, I guess. Let's see. Tycho Brahe he died in 1601. Interesting. So he didn't get to see the 1604 supernova. Very interesting. In his relation with Kepler. So yeah, that was around the time of Kepler. Where's Kepler at? Relations. A relation with Kepler. There we go. Kepler lived till 1630, and then Copernicus. Copernicus lived. Copernicus was 100 years before Galileo, Tycho, and Kepler. Copernicus died in 1543. So that's why he's always the more important out of all those, because he was so ahead of his time, really. So he died well before 1572 and 1604. Two landmark astronomical observations that were pivotal in breaking the mold set in stone by Aristotle, almost 2,000 years before that, well over 2,000 years ago for us. Aristotle essentially convinced everybody, because he was such a formidable intellect who was an expert over so many areas of inquiry. Around 300 BC, Aristotle convinced everybody that the cosmos, the firmament, was eternal and fixed in a way that is unchanging over all time. So the heavens were the realm of the, a realm of an entirely different nature than the Earth. The Earth was dynamic, and, we have all the, again, like I said, weather, climate, atmosphere, are changing geological features, rivers, oceans, everything's fluctuating. And Aristotle was firm that the heavens were firm. But these supernova actually were led to a paradigm shift. The observation of Mira combined with the supernovas 1572 and 1604 proved that the starry sky was not eternally invariable, as Aristotle had taught Europe to believe. In fact, for 1,000 years, it's interesting that Aristotle was known as the philosopher. So there was no one greater than Aristotle's opinion, which he turned out to be wrong in quite a few interesting ways. I think one of the more egregious examples of his what's the word? His carelessness, I guess, in claiming knowledge on something was that women had a different amount of teeth than men. So maybe his subject was just an unfortunate anomaly that he just used as the type for women's dentistry pre 1200. So yeah, in this way, Mira, I just wanted to bring it up because it's the textbook example of a variable star, and it's one of the first, if not the first, variable star. At first mistaken as a supernova or a nova, but once its variation, because novas kind of quickly brighten over just a couple days or weeks. Supernovas, they reach their peak and then gradually diminish, obviously to never return, because that's the nature. They're an exploding star, essentially. So the remnant might be a white dwarf, but it might be, faintly visible if it's close by. But unlike the variable star Mira here, supernovae don't ever increase and return back to a high level of luminosity. So this Mira directly contributed to the astronomical revolution of the 16th and early 17th centuries. So while some stars seem to increase, some stars seem to diminish in brightness, like Delta and Beta there, according to him, some stars have all at once blazed forth with great splendor, and after a gradual diminution of their light, again become extinct. The most remarkable instance of this kind is that of the star which appeared in 1572, in the time of Tycho Brahe. It suddenly shone forth, and this is a very famous supernova, one of only two that have ever actually, as far as we know, been observed in our own galaxy, the Milky Way. There have been plenty others, or, at least, I say many others, I guess, that we've seen in other galaxies since we've understood, just in the past 100 years, I guess. There's a famous one seen in 1987, for instance, but they've all been outside our galaxy. So that's, to me, that's very interesting that, we've yet to see since 1604 a supernova burst and blow up in our own galaxy. That's very cool. So it's on So this supernova SN 1572, which was known as Tycho's supernova, suddenly shone forth in the constellation of Cassiopeia. Cassiopeia, with a splendor exceeding that of all stars of the first magnitude, even Jupiter and Venus, the brightest regular objects, other than the moon and the sun, of course, but so at their least distances from Earth. So even the closest that Jupiter and Venus come to Earth, it was brighter than that. It could be seen with the naked eye on the meridian in, get this, full day. That's crazy. That's crazy. To imagine just seeing a star so bright, you could see it in full day. So that's what this, we didn't know it was a supernova at the time. They just thought maybe it was a new star or something. But so its brilliancy gradually diminished from the time of its first appearance, and at the end of 16 months it entirely disappeared. It's never been seen since. And it says here, see a more particular account of this phenomena on page 40. So I'm sure this is in the chapter on Cassiopeia. Yeah, Cassiopeia. Cassiopeia. I guess I like to say that better. Cassiopeia on page 40. Page 40, page 40, page 40. So it says 200 equidistant from the pole, exactly opposite of another remarkable star in the square of the Great Bear. See Magras, there we go. Interesting. So they mention our Magras, but it says so I guess Calf is a star in the... Man, there's so many little connections this is making right here, but Calf is in the garland of the chair, almost exactly in the equinoctial color. Points to Andromeda, but we'll be getting to that later. So in relation to this star, Calf, 55 stars in Cassiopeia, so it makes a very distinguishable constellation. But it says it also serves to mark a spot in the starry heavens, rendered memorable as being the place of a lost star. A lost star. That's such a magical concept. 250 years ago, a bright star shone 5 degrees north-northeast of Calf, shone where now is a dark void. Can you only imagine in terms of the mystical, just magical, spiritual existence that made up the world in the Middle Ages and prior, just how massive of an impact that might have had. Speaking of constellations and the relationship between the gods and the myths that are on those constellations, and how they influence the course of human events and our expectations of what's to come, and the goals we set, the things we fear and avoid, and the things we seek and hope for. And then imagine one of those fundamental elements in the firmament, the realm of the divine realm of the deities. Imagine that one day shining forth brightly in a sort of blaze of glory, only to fizzle out and never be seen from again. So in terms of a god, that would have been such an amazing, such a remarkable, so impactful, I bet. Thinking that one of the gods, one of the things that has always existed, one of the eternal beings, has just disappeared in a blaze of glory. And of course, humans being very familiar with fire for hundreds of thousands of years, for millions of years actually, it only seems natural that we would akin that to like a funeral pyre of a deity, some kind of divine funeral for a god. On November 8th, 1572, Tycho Brahe and Cornelius Gemma saw a star in the constellation of Cassiopeia, which became all at once so brilliant that it surpassed the splendor of the brightest planets. It might even be seen at noonday. Gradually this great brilliancy diminished until the 15th of March, 5 months later, when without moving from its place, it became utterly extinct. Its color during this time exhibited all the phenomena of a prodigious flame. First it was of dazzling white, then a reddish yellow, and lastly of an ashy paleness, in which its light expired. It's impossible to imagine anything more tremendous than a conflagration that could have been visible at such a distance. It was seen for 16 months. Some astronomers imagined that it would reappear again after 150 years, but it has never been discovered since. And this phenomenon alarmed all the astronomers of the age who beheld it, and many of them wrote dissertations concerning it. Reverend Professor Vince, one of the most learned and pious astronomers of the age, has this remark, quote, "The disappearance of some stars may be the destruction of that system at the time appointed by the deity for the probation of its inhabitants, and the appearance of new stars may be for the formation of new systems, for new races of beings then called into existence to adore the works of their Creator." Wow, imagine that. Just think, so this guy was positing that perhaps there was other gods, because he didn't say our Creator, he says there, maybe meaning that he had the notion that our God had a domain restricted to our star. And he continues, Burritt continues, "Thus, we may conceive the deity to have been employed from all eternity, and thus he may continue to be employed for endless ages, forming new systems of beings to adore him, and transplanting beings already formed into happier regions, who will continue to rise higher and higher in their enjoyments, and go on to contemplate system after system through the boundless universe." in the famous mathematician, astronomer Laplace, Simon Laplace, says, quote, "As to those stars which suddenly shine forth with a very vivid light, and then immediately disappear, it is extremely probable that the great conflagrations produced by extraordinary causes take place on their surface. This conjecture continues he, is confirmed by their change of color, which is analogous to that presented to us on Earth by those brilliant bodies which are set on fire and then gradually extinguished." Man, it's so interesting. Like, this is like a stepping stone into the past. This is 200 years old, talking about something itself 200 years prior to itself. So interesting, man. Okay, so back to chapter 13. Well, I guess we've made it to page 2. But I do want to add to the supernova because it was so important. Supernova 1572. So this is called Beta Cassiopeia 1572, or Tycho's supernova. So it is a type 1a supernova in the constellation Cassiopeia, one of 8 supernova visible to the naked eye in historical records. In this, again, one of only 2 that have ever been witnessed from our own galaxy. In the appearance of the Milky Way supernova in 1572, it belongs to one of the more important observations in the history of astronomy. Because this appearance, like we said, of this new star helped to revise ancient models of the heavens and to speed on the revolution in astronomy that began with the realization of the need to produce better astrometric star catalogs, the need for more precise astronomical observing instruments. And it challenged the Aristotelian dogma of the unchangeability in the realm of the stars. So again, on the scale, this was so bright that it went into the negatives in magnitude. It was a negative 4.0 magnitude star on November 16th, 1572 at its peak. And it remained visible to the naked eye early into 1574, gradually fading until it disappeared. And so what we know now, and this is, here's a picture of it, of the supernova right here. Let's see, what do we have here? And then, what was the distance to the star? 2.5. So it's 2.5 to 3 kiloparsecs, or 8 to 9,800 light years. A parsec to light year is roughly the equivalent of a yard to a foot. So 1 parsec is roughly 3 light years. So it's almost 10,000 light years away, still in our galaxy. It's been now, as we can see, observed optically, but it was actually first detected at radio wavelengths. And I hope you guys find this interesting too, because again, I love the intimate connection. I love understanding and knowing. And some of it, might be conjecture. with the astrology and all that, but I just have a love of seeing the big picture, and I love it when my two loves, history, one of my two interests, I guess, and astronomy, come together. And they do perfectly in this anecdote, this historical story from Ming Dynasty China. And this was obviously has to do with this supernova, so it was roughly around the year 1572 when the star became an issue between the chief secretary, chief consultant to the young Wanli Emperor. Wanli's father, the Longying Emperor, had died in 1572, actually, at only the young age of 35. The young 10-year-old young Emperor Wanli unfortunately inherited a country still in decline due to its corruption, primarily in the ruling class. But before long, but before the Longying Emperor, his father, died, Longying had instructed the chief minister, Zhang Juzang, the consultant, Zhang Juzang, to oversee the affairs of state and become the dedicated advisor to his little Wanli. And you can imagine a 10-year-old might need a loyal, dedicated, disciplined, conscientious, truthful advisor. So beginning in 1572, Zhang became mentor and regent during the early years of the reign of Emperor Wanli. He strongly influenced and guided him, and the Chinese government was under his temporary rule through his teenage years. But from the emperor's first ruling year, in accordance with the cosmological tradition, he was actually warned to consider his misbehavior, since the new star was interpreted as an evil omen. So right at the beginning of his reign, at 10 years old, this supernova, Tycho's supernova in 1572, had exploded and erupted. And of course, great civilizations are bound by the tradition of astrological observations and their integral effects on the narratives and the histories of their civilizations and their ancestors. So this was some sort of signal, and they took it, the Chinese took it as a evil omen. So while in temporary power, Zhang's reforms consisted of fiscal measures in order to address the persistent revenue shortage that plagued the government, an attempt to restore discipline to an increasingly corrupt bureaucracy. However, it seems the similarly strict upbringing that he also imposed on the emperor also aroused resentment, telling us that the Wanli Emperor, little Wanli, didn't heed the celestial warning of 1572, and after his death, Zhang's political opponents quickly accused him and Feng Bao of several major charges. Feng Bao, I guess, was an accomplice of Zhang's, helping him rule while Emperor Wanli was maturing. And the opponents, after Zhang's death, accused him of corruption, embezzlement, factionalism, and as a result, his family was purged, and his wealth and estate was confiscated on the Wanli Emperor's orders. Zhang's reputation would only be rehabilitated more than half a century later, just before the downfall of the Ming Dynasty. So little Wanli was actually the last descendant of the Ming dynasty. It was a great dynasty in, late, I guess maybe early Renaissance for us and over here in the Western world. And it's very interesting that he disregarded and discarded the disciplined leader and mentor of his, and he ended up in his own downfall. So there was a little, again, it's very, very interesting, the connection and correlation with how people interpret these distant events, cosmological phenomena, and we project, and then somehow, sometimes, these prophecies become self-fulfilling. Seems Zhang's efforts stood the test of time, while the Emperor Wanli's undisciplined behavior made his own dynastic lineage dissipate, just like the luminosity of the once bright star. So, let's see, I think we were, what do we go on to next? I think he says something about 1604. So let's see. So Burke goes on to talk about the second supernova. This called Kepler's supernova, and this was, of course, Tycho Brahe. He died in 1601. Kepler was his independent, but yet still Kepler's, under Tycho's financial tutelage, I guess. And Kepler studied under Tycho and stayed in his court and was financed by Tycho. Tycho being on top of an astronomer, also a minor ruler, royalty. And so it's kind of cool that there's a lineage there, and Tycho got one named after him, and 30 years later Kepler got one as well. Another instance of the same kind was observed in 1604, when a star of the first magnitude suddenly appeared in the right foot of Ophiuchus. It presented, like the former, all the phenomena of a prodigious flame, being at first of dazzling white, then reddish yellow, and lastly of a leaden paleness, in which its light expired. So these instances prove that the stars are subject to great physical revelations. And again, it's so amazing that this guy is, in the early 1800s, at the time this book was written, they hadn't even discovered Neptune yet. And they still, in this book called Uranus, Herschel, after the famous astronomer Herschel, who had discovered it just, 40 or 50 years prior to the writing of this book. So they don't know anything about the, I think maybe 15 years before this, in 1815, the first uses of spectroscopy had started. So where you look at the light coming from an object, you break it into its rainbow spectrum, essentially, to its different colors, and by filtering it through a prism, you're able to, like anyone who's taken a physics lab, you're able to discern different spectral lines. I'm trying to remember if they knew what those meant, but regardless, what they ultimately mean now is that they identify particular elements because each element, carbon, oxygen, give off and absorb light and photons at different wavelengths, depending on which element they are. I guess due to the way they interact with light when they get energized by heat and radiation, electromagnetic radiation, they get ionized, so their electrons get elevated to higher degrees, or sometimes they get stripped entirely of electrons. When they're given energy, they might absorb wavelengths of light at a certain color or wavelength, and then as they have a tendency for the electrons to fall back down to their preferred state, to anthropomorphize atoms, the act of the electrons going from a larger, further away outer shell, more energized, to a lower energy state shell closer to the nucleus of the atom, gives off protons at a specific wavelength of light that is unique to that particular element. So based on the atomic, subatomic particles, the number of protons and neutrons that interacts with light in such a way that it absorbs and emits particular, specific, predictable wavelengths of light. So looking at a star in this book in the early 1800s, they had just started this practice where they were filtering starlight. You can imagine how difficult that might be through filters because they're so, dim, and breaking them, starlight, up into their specific wavelengths of their spectral lines, and being able to discern the particular densities or ratios of what types of elements the stars are made up of, at least on the surface, the elements that are contributing to the emitted and received and detected light that the astronomers are looking at. So it's cool that, that gives you the context in which the astronomers are looking at the scientific, the level of knowledge of the heavens and stars and star evolutions at the time of the writing of this book, and they're working with the bare minimum evidence, yet he's able to make speculations that end up being very accurate, like, even though they're broad, but still, that the instances of supernova prove that stars are subject to great physical revolutions. We interpret that as life cycles nowadays. So in 1604, Kepler's supernova, SN 1604, type 1a supernova as well, also occurred in the Milky Way, in the constellation Ophiuchus. This is, so within 30 years of each other, roughly, and not since, it's been 420 years since our Milky Way, at least, I guess we could definitively say, unless, has seen a supernova, unless some crazy series of events allowed it to be hidden from our view, which that seems highly unlikely. So it's the most recent supernova in our galaxy to have been unquestionably observed by the naked eye, occurring no further than 6 kiloparsecs. So multiply that by 3 and we get light years. That's roughly, they're saying roughly, 18 to 20,000 light years from Earth, which is about the distance of us to the center of the Milky Way, Sagittarius. And prior to the adoption of the current naming system, it was named after Johannes Kepler, the German astronomer who described it in his book, his famous book, De Stella Nova. It was visible to the naked eye and brighter at its peak than any other star in the night sky, with an apparent magnitude of negative 2.5, so not quite the negative 4.0 of Tycho's supernova 1573. Or 72. It was visible during the day for over 3 weeks, and records exist beyond Europe, also in Chinese, Korean, and Arabic sources. And here we have Kepler himself actually drew from that book, De Stella Nova, the constellation depicting where in that constellation and the magnitude of the star. 8 grid squares down, 4 over from the left. And now before we get, so that's the extent of the variable stars. And then he's going to go on to talking about binary stars, but he directs us to page 41. So that's where I'm going to go. I'm going to follow Burritt's lead. And check out page 41. 41. Let's go. Right there. Okay. So this is just an extension of what we were reading earlier. And so, right under the quote from Laplace, we have a quote from Dr. Good. Can't be bad. The late eminent Dr. Good also observes that, quote, worlds and systems of worlds are not only perpetually creating, but also perpetually disappearing. And it's an extraordinary fact that within the period of the last century, not less than 13 stars in different constellations seem to have totally perished, completely disappeared. And 10 new ones seem to have been created. So, in many instances, it's unquestionable that the stars themselves, the supposed habitation of other kinds of orders of intelligent beings, together with different planets, by which it's probable that it's so tiny it's hard to read, that they were surrounded, by which it's probable that they're surrounded. So saying that he's speculating that most of these stars probably have planets themselves, which we now know is true. They've utterly vanished, and the spots which they occupied in the heavens have become blanks. What has befallen other systems will assuredly befall our own. Of the time and the manner we know nothing, but the fact is incontrovertible. It's foretold by revelation, it's inscribed in the heavens. It is felt through the earth. Such is the awful and daily text. What then ought to be done? What then ought to be the comment? The great and good Beza, falling in with the superstition of his age, attempted to prove that this was a comet, or the same luminous appearance which conducted the Magi, or the wise men of the East, into Palestine at the birth of our Savior. And that, get this, it's now appeared to announce his second coming. And then here, this is the supernova remnant from 1604. So at the time of the writing of this book, it was a little over 200 years old. So about 220, maybe 230, we'll say. Because this was written in 1833 originally. And he says about 6 degrees northwest of Kaf, the telescope reveals to us a grand nebula of small stars, apparently compressed into one mass or single blaze of light, with a great number of loose stars surrounding it. Then it goes into a history of Cassiopeia. Cassiopeia was the wife of Cepheus, king of Ethiopia. King of Ethiopia. And mother of Andromeda. She was the queen of matchless beauty, and seemed to be sensible of it, for she even boasted herself father fairer than Juno, the sister of Jupiter, or of Nereides, a name given to the sea nymphs. This so provoked the ladies of the sea that they complained to Neptune of the insult, who then sent a frightful monster to ravage her coast, as a punishment for her insolence. But the anger of Neptune and the jealousy of the nymphs were not thus appeased. They demanded, and it was finally ordained, that Cassiopeia should chain her daughter Andromeda, whom she tenderly loved, to a desert rock on the beach, and leave her exposed to the fury of this monster. She was thus left, and the monster approached, but just as he was going to devour her, Perseus killed him. And in Eusden's Ovid, the line is, quote, "The Savior youth, the royal pair confess, and with heaved hands their daughter's bridegroom bless." And speaking of Andromeda, I think on just a couple pages, yeah, there we go, Andromeda, right there. We'll eventually get to it. They talk about the little interesting nebula, oval shaped, in the Andromeda constellation that we know today to be the 2 million light year distant and comparably sized galaxy nearest to us. So this queer little nebulous, cloud of oval-shaped dust, oddly organized in a compact shape, with light peering through. I believe he said it, appearing as though it's being projected through a horn. This odd little, just a little side note that you can observe ends up being a massive galaxy right next door. Okay. So a great number of stars have been observed whose light seems to undergo a regular periodic increase and diminution or decrease. They're properly called variable stars. So he's saying that maybe the other ones we talked about were in that category. The nova certainly weren't, but and did he actually use the word nova? Did he? They didn't call it supernova, did they? Yeah, I don't think they did. So yeah, they didn't have the designation of supernova, but he's saying for certain, absolutely, these next stars down here he's about to mention, they fall in the category of regularly variable stars. One in the Whale has a period of 334 days, and it's remarkable for the magnitude of its variation. From being a star of the second magnitude, it becomes so dim as to be seen with difficulty through even powerful telescopes. Some are remarkable for the shortness of the period of their variation. For instance, Algol has a period between 2 and 3 days. Algol. Delta Cephei of 5 1/3 days. Beta Lyrae of 6 2/5 days. And Mu Antinoi of 1 week. And we can see here Algol is Beta in the constellation Perseus. So Beta Persei, known colloquially as the demon star, is a bright, multiple star in the constellation of Perseus, and one of the first non-nova variable stars to be discovered. I wanted to show you guys this one because it's really amazing how many stars can be gravitationally locked with one another. Because I think, a binary star is pretty cool, and then you add a third star in there, and it's like that seems like it would be an unstable orbit. Yet this Algol here, and we'll be coming across quite a few others, just as interesting, in my opinion, is a 3-star system. And we're going to see others with even more stars in them. So it consists of Beta Persei, AA1, AA2, and AB. So what that meant is that originally they thought it was a binary system, and of course as our lenses and our ability to observe get more and more fine-tuned and advanced, we're able to resolve sometimes entirely new stars orbiting these in what was a binary, now is a trinary system, multiple star system. So Algol is a three star system consisting of Beta Persei AA1, AA2 orbiting each other, and then that binary system is orbiting Persei AB, in which the hot luminous binary primary Beta Persei. Okay, so AA1 is hot and luminous and primary, meaning gravitationally dominant, more massive. And AA2, Beta Persei AA2, is cooler and fainter. And those two regularly pass in front of each other and cause an eclipse. So Algol's magnitude is usually near constant at 2.1, but regularly dips to 3.4, meaning larger magnitude number, larger number means fainter, every 2.86 days during the roughly 10-hour-long partial eclipses. And here we have I'll play it right now. Let's see. Yeah, super cool visual off Wikipedia. This is the interpolation of the orbit of AA2 around AA1. And the four, what's amazing is that the four frames at the top are transposed onto the graphic at the bottom. So that's real data, actual visual data that they collected. And then they're able to, I guess mathematically change the perspective so you can see what it might look like from, above the system. Algol between 2 and 3 days. So amazing. And then here we, above that I didn't address yet, we have the light curve of Delta Cephei, showing magnitudes versus pulsation phase. Pulsation phase. Let's see, what do we... Magnitude versus pulsation phase. I'm not sure what pulsation phase means. Let's see. So we have Algol. Here's a better visualization of it, I guess. Algol A and B, and then Algol C is more distant. And that's those are just the images without the graphics showing it. That's pretty amazing. That is pretty amazing. It says this animation was assembled from 55 images from the Chara interferometer in the near-infrared H-band, sorted according to orbital phase. Oh, okay, good. Because some phases are poorly covered, AA2 jumps at some points along its path, so we're not able to track it exactly every time, but so pulsation phase. So anyways, you can see its magnitude regularly increasing along its phase. In the ancient Egyptian calendar, and we're gonna bring this up in a later episode because I don't think I'm gonna be able to get into the binary clusters and nebulae today, or at least binary, because the second out of our 4 sections I was gonna cover today, now looks like I'm only gonna be able to do section 1. But is binary stars, or double stars, as Burritt called them. Without realizing that, most of the stars he put as variable stars do fall in that category because they are extrinsically variable, meaning that they appear to vary in luminosity just because of our vantage point. In other words, they wouldn't if we were looking at them, if our solar system was oriented such that we were above them and looking down, and therefore the binary or their planetary disks didn't obstruct our view of them. So it's just interesting that, again, one perspective of this is we're seeing how the science of astronomy has evolved. And as a testament to how old the known observation of Algol is, an ancient Egyptian calendar of lucky and unlucky days composed 3,200 years ago, so 1200 BC, which happens to actually be right around the time of the Bronze Age collapse. That real famous lecture by Eric Klein that's going around on YouTube. So it's interesting. But anyways, so this ancient Egyptian calendar of lucky and unlucky days, composed 1200 BC, is claimed to be the oldest historical document of the discovery of Algol. The association of Algol with a demon-like creature, the Gorgon, in Greek tradition, or ghoul in Arabic tradition, another word we get from them, suggests that its variability was known long before the 17th century. Oh, and then here I just had two examples of extragalactic supernova that we know about. Here's this one is supernova 1994 D, meaning it's the fourth one. A through C had already been seen. Look at this. This is a distant galaxy, and that bright spot is on the outskirts of the galaxy and is outshining the entire galaxy, its host galaxy that it's native to. It's just hard to really understand just how much power, energy goes into that. And then here's one from this year, actually. I forgot that it was. Supernova 2020 JFO from galaxy Messier 61, 52 million light years away. Taken by an amateur astronomer. So awesome, so awesome. Look at that, and all of these clouds are galaxies themselves. And that one little dot right there is the supernova, making itself distinguished and extinguished from the whole galaxy that it lived its life cycle in. Okay. And here we have just a graphic, not actual data, but a graphic of binary stars and how the brightness decreases as they eclipse each other. You can see it dips The small dip is when the small star passes in front of the large, dimmer star. The large dip is when the more luminous, tightly compacted star is eclipsed by the larger, less luminous star. So in other words, right at the base of the trough, right there, pretty much represents the solo, individual brightness and magnitude, luminosity of the large, probably red giant in this case, because it's completely covering the light from the smaller star. So, to finish up our section on variable stars here, God, I'm so happy with this book. This book's so awesome. Such a piece of history. So that was Algol, and then he, gives the other examples of the other short period variable stars. A few of which are binary themselves. Like, for instance, let me look up Delta Cephei. Yeah, Delta Cephei. Delta Cephei, I could show you guys right here, is the Bayer designation for a quadruple star system, so it has 4 stars, less than 1,000 light years away too. Pretty close in galactic terms. Extinction. At this distance, the visual magnitude of the star is diminished by 23%. As a result of extinction caused by gas and dust along our line of sight. In astronomy, extinction is the absorption and scattering of electromagnetic radiation by dust and gas between emitting astronomical objects and the observer. So this is and I should have recognized that too. That was dumb. This is the prototype of the Cepheid variable, which is monumental for the history of astronomy and humanity, really. Cepheid variable stars is the prototype for the Cepheid variable stars that undergo periodic changes in luminosity. So this was discovered to be variable by John Goodricke in 1784. It's popular. It's important. It's important because I know generally I was trying to get a more specific explanation, but generally it's important to history because it allowed Edwin Hubble to classify very accurately the true distance of, was it Andromeda Nebula? He was able to, based on the standard characteristics of this type of star, this specific type of variable star, known as a Cepheid variable, because of this particular one right here being the first of its kind found. It was in the Cepheid constellation, so that's how it got its name. Because of the predictability and regularity of luminosity, whenever one is found, essentially the time, the period, or its frequency of variation in luminosity is found to be directly proportional to its intrinsic brightness. So whenever one of these is found, as long as we have maybe through parallax, looking at it and physically being able to use geometry, mathematically, I guess, to determine its distance from us, we were able to have a standard candle and understand how bright or luminous a Cepheid variable appears at a specific distance. And once we knew that, we compared all other Cepheid variables to that one with a known distance. And Hubble found a Cepheid variable that he thought was a supernova until he observed it long enough and recognized that it didn't hit its peak and diminish forever like a nova would, but it actually had a Cepheid variable, a regular variable, a reoccurring variable luminosity, like all variable stars do. He then was able to recognize that was in a nebula or galaxy, and once he recognized that it fit the characteristics of a Cepheid variable, he was able to determine, based on its luminosity compared to a closer variable of known distance from us, that variable was not just hundreds or thousands of light years that most objects in the early up to the early 1900s were thought to be, but this was millions of light years away. So the discovery of a Cepheid variable allowed Hubble and other astronomers, but most famously Hubble, to essentially revolutionize our perception of how distant and then thereby vast the universe really is, and how distant objects like galaxies were, and if they really were millions, not just thousands, but millions and millions, maybe even billions of light years away. If we could see them at that distance, of course, that meant that guys like this were able to obviously figure out that they were large, but, make extraordinary leaps of scientific and astronomical hypotheses and theories about how the universe really works. So more specifically, again, it's just cool that he named it, as just an interesting star, interesting variable star that has a short period, as one of the most important sources of cosmic information about the fundamental workings of the universe. He says, Delta Cephei, which explains its brightness and noticeability, I guess, is among the closest stars of this type of variable to the Sun, with only Polaris being nearer. Its variability is caused by the regular pulsations in the outer layers of the star. It varies from magnitude 3.48 to 4.37, and its stellar classification also varies from F5 to G3. This pulsation period is 5.366249 days, to rise to a maximum, occurring quicker than the subsequent decline to minimum. So because of the period of this class of variable is dependent on the star's luminosity, Delta Cephei is of particular importance as a calibrator of period luminosity relationship, since its distance is now one of the most precisely established for a Cepheid. And I always wondered, because you always hear that when you're hearing about Hubble's breakthrough discovery of the universe and its size and galaxies. Because before that, we thought the universe was just one mass of stars. We thought essentially the Milky Way galaxy was all there was. We thought everything we saw in the sky was a part of our gravitationally bound group of, galactic stars. We didn't consider a galaxy as a individual island grouping of stars that is just one of trillions out there. And so that was a phenomenal leap, but they always kind of seem to gloss over in popular science the method in how Cepheid variables actually were able to tell, scientifically speaking, how distant, they were. And that's it, is that somehow they have a very stable and predictable and reoccurring relationship between how bright they get and the duration, the time it takes from each peak of brightness it takes to undergo one cycle of variability in brightness, essentially. And because it's so close, when Earth is going around the sun, when Earth is on opposite sides of our orbit, we're able to look at the star, and then 6 months later, look at it again from a distance of twice the radius, or one diameter, one orbital diameter away from where we measured it 6 months prior, being about roughly 190 million miles apart, I guess. That gives us enough of a change in position in the cosmos to see a tiny shift of the star's position with respect to much further, much less changing stars in the background. To finish up our section on variable stars, the regular succession of these variations precludes, meaning prevents, the assumption of the supposition of an actual destruction of the stars. Neither can the variations be supposed to arise from a change of distance, for as the stars invariably retain their apparent places, it would be necessary to suppose that they approach to and recede from the Earth in a straight line, which is very improbable. In other words, for the change in luminosity of the variable stars to be explained by a change in distance, like a car headlight gets brighter when it's coming toward us, that would mean just that it is like traveling down a highway towards and then from us in a variable pattern, which is very unlikely that a star, orbiting with, all these other stars, this one particular star just happens to be oscillating in a perfectly straight line. I like how he uses practical reasoning like this, saying it would have to be moving away and towards us in a perfectly straight line, because it doesn't, from our reference frame, it isn't moving with respect to the background stars at all. Except for really close stars like Alpha Centauri and the Cepheid variable that we're able to very minutely, subtly detect. I just love that he's showing how astronomers originally reasoned, and nowadays we have advanced technology to confirm the results of the right reasoning earlier, but back then you had some data, very limited, with very crude telescopes, for the most part, relative to, orbiting telescopes like the Hubble nowadays. And you had to use logic and rational lines of reasoning to guess and theorize. And that's something that a lot of these modern textbooks fail to do, I think. I think teaching comes best from understanding how we arrived at all this information that we apparently know about the universe. And when you just dump it on a first-year student as though it's all self-explanatory, I think that kind of discourages people from wanting to engage in critical thought, The most probable supposition is that the stars revolve like the suns and planets, like the sun and its planets, about an axis. Such a motion, says the elder Herschel, who discovered Uranus, may be as evidently proved as the diurnal motion of the earth. Dark spots, or large portions of the surface, less luminous than the rest, maybe, turned alternately in directions either towards or from us, rotating, will account for all the phenomena of periodical changes in the luster of the stars. So satisfactorily they'll account for this that we certainly need not look for any other cause. And there we go. That's a great example of bad reasoning. So Herschel was so convinced that because we saw some spots on our own sun, all the other stars must have them, and they might. But he was so convinced that that was a good enough solution to the issue of variability in stars' brightness that this guy picked up on it, because Herschel was a prominent figure in astronomy. And so he hadn't really considered that, perhaps there was more dynamic phenomena that are intrinsic to the star, or maybe that there are entire stars, other stars orbiting the systems that are eclipsing the star itself, making it dimmer, and all the other ideas we talked about being whether it's nebulae or nebulous protostellar clouds of matter orbiting, protoplanetary, I guess, clouds of matter orbiting the star. And what was the other one? I guess just like Cepheid variables, outer layers that are just periodically oscillating in luminosity. So I guess that about will wrap it up for today with our section on variable stars. Thanks again to my sponsor, Manta Sleep. Where did I put that thing? I hope you guys do try them out. They're really just a wonderful product. So, to be honest, I'll gladly promote them anytime in the future. And there were also a nice little cherry on top was that the representative I was working with she was very, very pleasant to talk to. So, I guess this is a better view here. You guys can see it. got a nice little Velcro strap. A little too loud to open now, but you can adjust it. Their phrase is infinitely adjustable, and that is true. You can make it fit you exactly. It's super comfortable, and the material super soft, very soft. So anyways, that does it for part 1 of 4, at least of 4 sections. You know, maybe I'll try to do more than one section in the next video, but until then, as always, thanks for tuning in, guys. I don't know why I say that, as always. I do enjoy all your comments. You liking the video, subscribing, obviously, lets me know you enjoy the content. I really thrive off compliments and feedback and constructive criticism. So you guys let me know what you liked, what you didn't, and I'll see you guys next time while we're figuring out more about astronomy from 1836.